Far beyond Neptune, a lonely world traces an impossible path. This is Sedna, a dwarf planet with an orbit so stretched out it defies all previous maps of our solar system. By the end of this journey, you will understand how this single frozen world is forcing us to redraw the boundaries of our own cosmic neighborhood. Its bizarre, 11,000-year-long journey hints at a hidden structure at the very edge of our sun's influence, a place known as the Inner Oort Cloud. What ancient forces could have sculpted such a solitary path, and what other secrets are waiting in the dark? What does it mean to discover a new frontier in your own backyard? The discovery came on a routine November night in 2003. Astronomer Mike Brown and his team were reviewing images from the Samuel Oskin telescope, an instrument specifically designed to scan vast swaths of the sky with relentless precision. They were hunting for slow-moving points of light, the telltale sign of distant worlds, and then they saw it, a tiny speck drifting against the backdrop of fixed stars. Initial observations confirmed it was a substantial body, but the real shock arrived with the first orbital calculations. As the data points connected, they traced a line so elongated it seemed to defy the orderly clockwork of the outer solar system. This was not just another Kuiper Belt object. Its predicted path swung so far out that the sun would shrink to little more than the brightest star in its sky. They named this lonely traveler Sedna. The immediate reaction among planetary scientists was a mixture of profound excitement and utter disbelief. The numbers suggested an aphelion, its farthest point from the sun, at a staggering distance. This was a realm where no known planet's gravity should hold sway. Finding Sedna was like meticulously mapping a coastline only to discover a lighthouse shining from miles out at sea, in waters you never knew existed. Its very existence challenged the textbook definition of our solar system's edge. The Samuel Oskin telescope had provided the technological window, but Sedna presented a cosmic riddle. How could such a large object achieve such a solitary and stretched-out orbit, and what did its presence imply about the darkness beyond? The hunt for answers was just beginning. Sedna's path is a cosmic ellipse stretched to its absolute limit. Think of a rubber band pulled taut between two fingers, where one finger represents the sun. Sedna spends most of its incredibly long life at the far end of that stretch, in the deep freeze of the outer darkness, only to swing in for a relatively brief, fleeting visit to the inner solar system before being flung back out again. This entire cycle, one single lap around the sun, takes approximately 11,400 years. To grasp that timescale, consider that the last time Sedna was at its closest point to the sun, our world was in the throes of the last ice age, and human civilization as we know it had not yet begun. Right now, it is on its long, lonely outbound journey, already more than 3 times farther from the sun than Neptune. This is nothing like the orderly, nearly circular orbits of the planets, which travel around the sun like cars on a racetrack. Even Pluto, once considered the outlier, has an eccentric orbit, but it pales in comparison to Sedna's extreme path. Pluto's journey still keeps it within the known disk of the Kuiper Belt, a realm bustling with other icy objects. Sedna, by contrast, ventures into a desolate void where the sun provides little more light than a full moon on Earth. Its incredible isolation is the key to the mystery. An orbit this stretched and solitary cannot be easily explained by the gravity of the planets we know. It is a celestial fossil, a preserved record of a violent event from the solar system's earliest days, pointing a steady finger toward an unseen and vast population of objects in the darkness beyond. For decades, our solar system's map had 2 clearly marked regions for its frozen leftovers. Just beyond Neptune lies the Kuiper Belt, a bustling, donut-shaped disk of icy worlds and comets, a cosmic junkyard where Pluto reigns as king. This is the frontier we thought we understood, but far, far beyond that, starting perhaps 1,000 times farther out, theoretical models predicted the Oort cloud. Imagine a vast spherical shell of trillions of icy bodies enveloping the entire solar system, a remnant of the Sun's original birth cluster, so distant that the Sun's gravity barely holds them. The space between these two zones was thought to be a largely empty no man's land. This is why Sedna's position is so deeply problematic. It does not fit in the Kuiper Belt, as its orbit carries it far too high above the flat plane of that disk. Yet it does not travel far enough out to belong to the classical Oort cloud. Sedna is a cosmic orphan, permanently stuck in the gravitational badlands between these two great reservoirs. Its very existence suggests that this vast emptiness is not empty at all. It hints at a bridge, a previously unknown structure now called the Inner Oort Cloud, a region populated by countless objects on similarly stretched orbits. Finding one was like discovering a single, ancient road in a desert we believed was completely barren. It forces us to ask, if this road is here, where does it lead and who else is traveling on it? Sedna's orbit presents a fundamental puzzle that begins with its closest approach to the Sun. This point, called its perihelion, lies at a distance of about 76 astronomical units. 1 astronomical unit is the average distance from Earth to the Sun. This means that even at its most intimate moment with the Sun's warmth, Sedna is still more than twice as far out as Neptune. This single fact is why it cannot belong to the classical Kuiper Belt. The entire structure of that belt is sculpted by Neptune's gravity, which shepherds objects into specific orbital families through repeated, gentle tugs over billions of years. But Neptune's influence effectively ends around 50 astronomical units. Sedna never gets close enough to feel that gravitational hand. It is, in the most literal sense, detached. It lives in a region of gravitational quiet, a cosmic eddy where the giant planets cannot reach. This isolation is its defining trait. While most Kuiper Belt objects are like commuters in a busy city, constantly jostled by the gravitational traffic of Neptune, Sedna is a lone sailor on a vast, placid sea, following a course set in the ancient past. Its path is so stable and so removed from the planetary system's hustle that it cannot have achieved this orbit recently. This forces a profound realization. Sedna is not a visitor from the Kuiper Belt that was kicked out. It is a permanent resident of a different, more distant neighborhood, and its presence implies that this quiet zone is not empty, but filled with a hidden population of such detached objects. The question then becomes, if Neptune did not put it there, what immense force could have possibly placed this fossilized world on its solitary path so long ago? The solution to this cosmic puzzle lies in a place that, until recently, existed only in theory. Astronomers call it the Inner Oort Cloud, or sometimes the Hills Cloud. Picture a vast spherical swarm of icy bodies, a transitional zone beginning just beyond the Kuiper Belt's outer fringe. This is not the distant, loosely bound Oort cloud of textbook diagrams, but a much denser and more structured region acting as a gravitational bridge between the known and the unknown. For decades, it was a necessary idea, a mathematical prediction to explain where certain comets might originate, but we had no direct proof it was actually there. Sedna changed everything. Its impossible orbit is not an anomaly, it is a perfect fit. This lonely world behaves exactly as an object born within that hypothesized inner cloud should behave, forever tracing a path that never brings it close enough to the planetary region to be disturbed, yet never allows it to escape entirely into the deepest dark. Finding Sedna was like unearthing a single, perfectly preserved bone from a creature we had only ever imagined. That one fossil provides undeniable evidence that the entire species existed. It transforms the Inner Oort Cloud from a speculative dotted line on a map into a tangible, physical frontier. This makes Sedna's discovery truly revolutionary. It is not merely a new world. It is a key, the first observational evidence unlocking a hidden chapter of our solar system's architecture, and confirming that our cosmic backyard is far more structured and far more populated than we ever dared to believe. But a single key can sometimes open more than one door. Another compelling theory has emerged to explain Sedna's lonely path, one that involves a ghost planet lurking in the solar system's dark periphery. This is the hypothesis of Planet 9, a world potentially 10 times the mass of Earth, tracing a colossal, slow orbit thousands of times farther out than our own. The gravitational pull of such a hidden giant could act as a cosmic shepherd. Over immense stretches of time, its gentle but persistent tug would sculpt the orbits of smaller objects like Sedna, herding them into the strange, clustered, and detached paths we observe. It would be like an unseen choreographer directing the motions of distant dancers from the shadows of the stage. This idea stands in stark contrast to the Inner Oort Cloud explanation. The cloud hypothesis suggests Sedna is a native resident of a vast, populated structure, its orbit a natural product of the solar system's initial formation. The Planet 9 theory, however, paints a different picture. It proposes that Sedna is an immigrant, its path artificially sculpted and maintained by the ongoing influence of a massive neighbor. The distinction is crucial and creates a vibrant scientific debate. Each theory makes different predictions. If the Inner Oort Cloud is the answer, astronomers should eventually find a whole population of detached objects with orbits oriented randomly, like a scattered swarm of bees. But if Planet 9 is the sculptor, these objects should show a distinct clustering, their orbits aligned in space as if they are all avoiding the same gravitational hand. For now, the evidence is tantalizing but incomplete. The hunt for more Sedna-like objects continues, each new discovery offering another clue. Is our solar system's edge defined by a vast, structured cloud of ancient ice? Or is it patrolled by a solitary, unseen giant whose gravity writes the rules for the darkness? The quest to solve Sedna's riddle is fundamentally a quest to choose between two radically different maps of our own cosmic home. Its surface is a testament to deep cosmic cold. Sedna itself is a small, dark world with a diameter estimated at roughly 1,000 kilometers, making it only about a third the size of Pluto. This places it in the category of a dwarf planet, a solitary ruler of a vast and empty kingdom. Its most striking feature is its color, a deep, dark reddish hue that stands out even among the other ruddy worlds of the outer solar system. This crimson tint is not merely for show. It is the signature of complex chemistry occurring over billions of years. The faint, weak sunlight at that incredible distance provides just enough energy to break apart simple molecules like methane ice on its surface. These fractured pieces then recombine into long, complex chains of carbon-rich molecules known as tholins. These tholins are essentially primitive organic compounds, the same kind of reddish, tar-like substances thought to be the building blocks for the chemistry of life elsewhere. So Sedna is not just a frozen ball of ice and rock. It is a museum piece displaying the results of a slow, patient chemical experiment conducted in the ultimate deep freeze. The conditions on its surface are almost beyond human comprehension. Its rotation is incredibly slow, with a day lasting about 10 hours, but this slow spin is the least of its oddities. Because it is so far from the Sun, its surface temperature is one of the lowest ever measured in the solar system, hovering just 40 degrees above absolute zero. At such cold, the very air we breathe would freeze solid into a blanket of snow. This is a world so frigid and ancient that its surface has likely remained utterly unchanged since the solar system's earliest days, a pristine relic from a time before the planets even finished forming. It is a frozen time capsule, and its reddish color is a cryptic message written in the language of primordial chemistry, waiting for us to decipher its meaning. The passage of time on Sedna is a story of profound extremes, where our earthly understanding of days and years completely unravels. A single rotation of this lonely world, one Sedna day, takes approximately 10 hours, not so different from our own. For a brief period, a dim, cold sun would crawl across its deep red sky, but the true scale of its existence is measured in years, and here the numbers defy all intuition. One complete orbit around the Sun, a single Sedna year, spans roughly 11,400 Earth years. This means that since its last closest approach to the Sun, human history has witnessed the entire rise of civilization, from the first agricultural settlements to the dawn of space exploration, all within one of its fleeting summers. That brief, relatively warmer period when it swings into the inner reaches of its orbit might last for a few centuries, a mere blink in its cosmic calendar. During this time, the Sun, though still a distant pinpoint, would shine with the intensity of a few hundred full moons, barely providing a whisper of heat. Then comes the long, slow fall into winter. For thousands upon thousands of years, Sedna recedes into the deep freeze, its sun shrinking to just another bright star in an endless black sky. The concept of seasons becomes almost meaningless when your winter is longer than all of recorded human history. This is a world where the ice age never ends, a realm of perpetual and deepening cold where the very rocks might crack from the strain of the chill. To stand on its surface would be to experience a silence and a solitude that is almost beyond human comprehension, a witness to a timescale that makes our own lives seem like a single, fleeting heartbeat in the grand symphony of the solar system. Sedna was not destined to remain a solitary mystery for long. The hunt was on for other cosmic recluses, other inmates of this distant prison astronomers now called the Inner Oort Cloud. These hypothetical objects earned a playful nickname, Sednitos, little Sednas, and they began to appear. In 2012, astronomers discovered an object designated 2012 VP113, informally nicknamed Biden. Its orbit was a stunning confirmation, another stretched path that never ventured close enough to Neptune to be influenced, with a perihelion of about 80 astronomical units. Then came an even more extreme object, officially named Lelekuanua. This world takes its name from a Hawaiian creation chant, evoking a life born in the darkest, coldest depths of the ocean, a perfect metaphor for its origin. Its orbit is so vast that a single year lasts over 30,000 Earth years, and it never comes closer than about 65 astronomical units from the Sun. It is arguably the most detached object we have ever found. Each of these discoveries is a monumental achievement, like spotting a single, specific grain of sand on a beach from miles away. They are not mere curiosities, they are data points, crucial pieces of evidence that allow scientists to move from a theory to a map. Finding one strange object could be a fluke, but finding a small family of them, all sharing the same detached characteristics, confirms a pattern. It tells us that Sedna is not a lone anomaly. It is the first identified member of an entirely new class of solar system object, the Inner Oort Cloud population. Every new Sednito discovered helps astronomers triangulate the invisible boundaries of this hidden realm. The precise orientations and tilts of their orbits are like subtle gravitational whispers, hinting at the overall shape and density of the cloud they call home. With each new discovery, the faint outline of this new frontier grows a little sharper, transforming our understanding of the solar system's true scale from a simple map into a living, three-dimensional structure. Detecting a world as dark and distant as Sedna is a feat of engineering that borders on the miraculous. To even see it, astronomers must push technology to its absolute limits. The initial discovery relied on wide-field survey telescopes, instruments designed to scan huge portions of the sky night after night, hunting for any single pixel of light that dares to move against the static background of stars. But once found, the real challenge begins. How do you study an object so faint that its light is billions of times weaker than what the human eye can perceive? The answer lies in the world's most powerful observatories. Giant telescopes like Keck in Hawaii or Subaru use mirrors the size of a small house to collect every precious photon of light that has traveled for hours across the solar system. These are not simple cameras, they are colossal light buckets gathering the faintest whispers from the cosmic dark. To understand its composition, scientists turn to a technique called spectroscopy. Imagine passing sunlight through a prism and seeing it split into a rainbow. Now, imagine doing that with a single, faint point of light that is Sedna. Every chemical element and molecule on its surface absorbs specific, unique colors from that rainbow, leaving behind dark fingerprints in the spectrum. By carefully analyzing these missing colors, a spectrometer can tell us from billions of miles away that Sedna's surface is covered in water ice, methane ice, and complex, reddish organic compounds called tholins. This is not magic, it is the power of applied physics allowing us to perform a chemical analysis on a world we will likely never visit. Space-based observatories like the Hubble add another critical layer. Freed from the distorting blanket of Earth's atmosphere, Hubble can obtain exquisitely clear images and spectra, providing a level of detail that is simply impossible from the ground. These technological marvels work in concert, transforming a single, moving pixel into a world with a known size, a known composition, and a profound story. They are our remote senses, extending human curiosity across billions of miles of empty space to read the secrets of a frozen fossil in the void. So how did this frozen world end up in such profound isolation? The explanation for Sedna's orbit must account for two seemingly contradictory facts. It was flung out to an immense distance, yet its orbit remains bound, never escaping the sun's grip entirely. This delicate balance points to a dramatic event in the solar system's infancy. The leading theory involves a cosmic game of gravitational pinball that occurred over 4 billion years ago. Our sun was not born alone. It formed within a dense cluster of thousands of other stars, all packed relatively close together. In this stellar nursery, close encounters with sibling stars would have been common. Picture the young solar system, its planets still coalescing, surrounded by a vast cloud of leftover planetesimals. As another star passed nearby, its gravity would have reached into this cloud like an invisible hand, violently stirring its contents. Some icy bodies were slung completely out of the solar system, lost to interstellar space. Others, like Sedna, received a gentler but still powerful kick. They were nudged onto vast, stretched-out orbits that never again brought them close to the planets, yet remained tethered to the sun. This stellar flyby theory elegantly explains the existence of the entire Inner Oort Cloud, not just Sedna. It provides the perfect mechanism to populate that gravitational bridge with countless frozen fossils. But it is not the only suspect in this ancient mystery. Another compelling scenario involves the giant planets themselves. Early in their history, Jupiter, Saturn, Uranus, and Neptune may have undergone a period of planetary migration, shifting their positions in a great gravitational dance. As they moved, their shifting gravity would have scattered the primordial disk of icy debris. Some objects were ejected outward, and a fraction of those could have been captured into stable, detached orbits just like Sedna's by the subtle gravitational influence of the galaxy itself. There is an even more dramatic possibility, the idea of a rogue planet. What if a fifth giant planet, similar in size to Neptune, once orbited our sun? During the solar system's chaotic youth, gravitational interactions could have hurled this world entirely out of the solar system. In its violent ejection, its gravity would have plowed through the outer disk, flinging a trail of objects like Sedna into their current orbits before the rogue planet itself vanished into the galactic dark. Each of these theories leaves a different gravitational fingerprint on the population of distant objects we are now discovering. The specific shapes and groupings of their orbits are clues that point back to the specific event that created them. Unraveling Sedna's origin is therefore a form of celestial archaeology, allowing us to peer back in time and witness the dynamic, often violent, processes that shaped our solar system's deepest frontiers. Sedna's lonely orbit is more than a curiosity. It is a direct challenge to the clean, orderly story we once told about the birth of our solar system. For decades, the standard model depicted a protoplanetary disk of gas and dust around the infant sun that was relatively compact, with its outer edge not too far beyond the orbit of Neptune. Planet formation was thought to be a local process, with worlds growing peacefully from the material in their immediate vicinity. The discovery of this distant fossil shatters that image. To explain how an object as large as Sedna ended up so far away, we must now accept that the Sun's primordial disk was far more expansive and massive than anyone guessed. It stretched out into a vast reservoir of icy planetesimals, a cosmic hinterland rich with the raw materials for building worlds. The presence of the Inner Oort Cloud, which Sedna represents, implies that this disk did not simply end. It faded gradually into a structured cloud of debris that reaches nearly halfway to the next star. This forces a dramatic revision of our solar system's blueprints. We are no longer looking at a neat, compact system with a defined outer boundary, but at a sprawling metropolis whose suburbs extend into an unimaginable darkness. The process of planet formation could no longer have been entirely peaceful. Sedna's exile is a testament to a violent and dynamic youth. The gravitational interactions that flung it outward required immense energy, suggesting a period of true chaos in the early solar system. Picture a crowded construction site where the giant planets were still settling into their final positions, their shifting gravity hurling countless building blocks in all directions. Some of this material crashed into the inner planets, perhaps delivering the water that fills our oceans. A vast amount was ejected entirely, becoming rogue planets and asteroids drifting between the stars. And a precious few, like Sedna, were given a gentler but still decisive push, sentenced to a permanent existence in the deep freeze, yet forever bound to the sun. This new narrative transforms our understanding. We are not the product of a quiet, isolated birth. Our solar system is the survivor of a turbulent and explosive beginning, and Sedna is one of its most enduring witnesses, a permanent reminder that our home in the cosmos is far larger and far more dramatic than we ever dreamed. This frozen world is more than just a distant relic. It is a vital piece in the puzzle of our own planet's history, a history written in the ice and fire of comets. Sedna's existence in the Inner Oort Cloud gives us a tangible anchor point for understanding one of the solar system's most dramatic phenomena, the arrival of long-period comets. These spectacular visitors, with their brilliant tails stretching across the night sky, originate from the deepest reaches of the Sun's gravitational domain, the theoretical Outer Oort Cloud. This is a spherical shell of trillions of icy bodies so far away that the Sun is just a bright point of light, and its gravitational hold is incredibly weak. For most of their existence, these comets drift in a state of frozen suspension. But what stirs them from their slumber and sends them on a million-year fall toward the inner solar system? The answer lies in the gentle, persistent tides of the galaxy itself. As our solar system orbits the center of the Milky Way, it does not travel on a perfectly smooth path. It bobs up and down through the crowded plane of the galaxy, and it occasionally drifts close to other stars. Each of these galactic interactions acts like a slight gravitational nudge on the outermost comets. It is the equivalent of gently shaking a tree laden with fruit. A few of the loosest apples will detach and fall. In this cosmic analogy, the comets are the apples, and the shake from a passing star or a galactic tide is enough to dislodge them from their tenuous orbits in the Outer Oort Cloud. Once freed, they begin their epic journey sunward, accelerating into the void. This is where Sedna's role becomes so crucial. By confirming the structure of the Inner Oort Cloud, Sedna helps astronomers model the dynamics of this entire distant reservoir. We can now better simulate how those initial galactic nudges cascade through the cloud. how some comets are redirected toward us while others are flung out into interstellar space forever. This is not merely an academic exercise. These same long-period comets, whose paths are dictated by the very cloud Sedna inhabits, have likely shaped the destiny of life on Earth. It is a sobering thought that the same gentle gravitational tides of the galaxy that might have guided Sedna into its orbit could also, millions of years later, direct a mountain of ice and rock onto a collision course with our world. The story of Sedna is therefore inextricably linked to our own, a distant reminder that the quietest, most isolated corners of our solar system still hold the power to reach across the void and touch us all. The dream of sending a spacecraft to Sedna is a journey that would dwarf every deep space mission humanity has ever attempted. A probe launched today, even with the most efficient trajectory and a gravity assist from Jupiter, would take well over 10,000 years to reach its distant target. This is not a simple matter of packing more fuel. It is a fundamental challenge of distance and time that pushes against the very limits of human ambition and engineering. To even contemplate such a voyage, we would need propulsion systems that are still in their infancy, like powerful nuclear electric engines or experimental solar sails, capable of accelerating a craft for decades on end to shave mere centuries off the travel time. The spacecraft itself would need to be a marvel of self-sufficiency, powered by long-lived nuclear batteries because solar panels would be utterly useless in a realm where the sun is a faint, cold star. Its computers and instruments would have to survive the relentless decay of deep space radiation for millennia, operating with a level of autonomy we can barely conceive because a signal from Earth would take over a week to reach it one way. Compare this to the New Horizons mission to Pluto, a triumph of modern exploration that took 9.5 years to reach its target. A trip to Sedna makes the Pluto flyby look like a quick jaunt to the neighborhood park. The communication delay with New Horizons was a manageable 4.5 hours each way, allowing for near real-time control from Earth. With Sedna, that delay stretches to days, meaning the spacecraft would have to navigate its own close approach, manage its instruments, and respond to any anomalies completely on its own. It would be the most isolated machine ever built, a single, intelligent speck executing a pre-programmed ballet in the dark, with its human creator's generations removed by the time it phoned home. Yet the scientific payoff would be nothing short of a bonanza. Flying by this frozen fossil would be like opening a time capsule sealed at the birth of the solar system. We could map its mysterious reddish surface in stunning detail, directly sample its primordial ices and complex tholins, and measure its feeble gravity to learn about its internal structure. Every byte of data returned would rewrite our understanding of the solar system's raw materials and the violent processes that sculpted its outermost frontiers. To visit Sedna would be to touch a piece of our own cosmic origin story, a prize so profound it continues to fuel our imagination, daring us to build a ship that can outlast civilizations. The name Sedna carries a profound weight, drawn not from a dusty textbook but from the rich mythology of the Inuit peoples. It belongs to the powerful and fearsome goddess of the sea, the master of all marine mammals who dwells in the frigid depths of the Arctic Ocean. This was a deliberate and inspired choice, just as the goddess Sedna rules a cold, remote, and life-sustaining realm. So too does this distant world govern a dark and mysterious ocean of space. The naming connects ancient human understanding of the untamable wilderness to our modern exploration of the cosmic deep, a poetic bridge between terrestrial myth and celestial reality. This distant speck of rock and ice, once just a dataset in an astronomer's log, was suddenly imbued with a soul, a story of creation, loss, and power that resonates across cultures. It transformed the object from a scientific specimen into a character in a much larger human narrative, a celestial body with a personality born from the very elements it represents: cold, isolation, and ancient mystery. This act of naming is never just a label. It is the first step in a discovery becoming part of our collective imagination, a process where science and storytelling inevitably intertwine. The cold, red world at the edge of everything had found its myth, and with that myth it began to inspire. Science fiction writers were among the first to seize upon its potential. In novels and short stories, Sedna has become a compelling setting for tales of extreme isolation, long-duration missions, and encounters with the primordial unknown. It is portrayed as a way station for humanity's future expansion, a frozen outpost where the rules of society are rewritten under a dim sun, or even as the home of ancient, alien artifacts preserved in the ultimate deep freeze. Its 11,000-year orbit provides a natural canvas for epic stories of generational ships and civilizations that rise and fall within a single celestial season. Artists, too, have been captivated, visualizing its deep red surface under a sky dominated by a faint, star-like sun, creating paintings and digital art that try to capture the profound loneliness and stark beauty of a place where the very concept of a day is alien. These creative works do more than just entertain. They perform a vital function, translating the dried data of orbital mechanics and spectroscopy into visceral human experiences. They allow us to feel the chill of that world and to grapple with the immense scales of time and space that it represents. When a scientist calculates Sedna's orbit, they define its path. But when a writer sets a story there or an artist paints its sky, they give us a reason to care about the journey. This public fascination, sparked by a single discovery, creates a powerful feedback loop. The more Sedna captures our imagination, the more we support the science that searches for its neighbors, that strives to understand its origin. We are not just mapping empty space. We are populating a new frontier of our mythology, proving that every time we push the boundaries of our knowledge, we are also expanding the boundaries of our dreams. The debate over Sedna's origin is a scientific tug-of-war with the solar system's history at stake. On one side, the Planet 9 hypothesis gains strength from a peculiar pattern. Astronomers have not just found a few oddballs like Sedna. They have discovered a small collection of extreme trans-neptunian objects whose orbits are not just stretched but also tilted and clustered in space. It is as if an invisible giant is herding them, its gravity forcing their farthest points to line up in a way that random chance simply cannot explain. This clustering is the primary evidence for a hidden world, a planet large enough to orchestrate this distant celestial dance from the shadows. The hunt for this phantom planet involves scanning the darkest, emptiest parts of our sky, searching for a single, slow-moving dot that would confirm its existence. Yet for all its explanatory power, Planet 9 is still a ghost, a mathematical prediction waiting for a direct sighting. The opposing view needs no such unseen giant. The Inner Oort Cloud theory argues that Sedna and its kin are not the product of a modern shepherd, but ancient survivors from a time when the sun's birth cluster scattered countless icy bodies into these detached orbits. Their very existence, regardless of their orientation, is the evidence. This theory suggests we are seeing the natural population of a vast reservoir, a structure that formed naturally as the solar system itself was born. The randomness of some of their orbital angles seems to challenge the need for a single, organizing force like Planet 9. Why would a massive planet allow some objects to escape its gravitational choreography? This is the core of the live, active debate that currently divides planetary scientists. Each new discovery of a distant object is now scrutinized for which side it supports. Does its orbit fall neatly into the predicted cluster, strengthening the case for Planet 9? Or does it break the pattern, suggesting a more random and populous Inner Oort Cloud? The next telescope observation, the next faint pixel of light discovered in the archival data, could be the one that finally tips the scales. We are witnessing a cosmic mystery unfold in real time, where the answer does not yet exist in a textbook, but is being written with every new glimpse into the dark. For all we have learned about this distant wanderer, Sedna remains a world defined by its mysteries. Its exact size is still a subject of debate, with estimates relying on assumptions about its surface brightness that could be wrong. We do not know its mass at all because no moon has been found orbiting it to allow that crucial measurement. Without mass, we cannot calculate its density, and without density, its very nature remains hidden. Is it a rocky world with a thick mantle of ice, or a more porous body of ice and rock, a fragile relic from the dawn of time? This single, missing piece of data holds the key to understanding its fundamental composition. The deep red color of its surface tells a story of complex chemistry, but we can only read the broadest strokes from here. Our spectrometers have detected water, ice, and methane, but they cannot tell us how these materials are arranged. Is its landscape a uniform blanket of reddish sludge, or are there craters with exposed, pristine white ice hidden beneath, cliffs of frozen methane, or vast plains of tar-like organics? Every pixel of light we gather is a blend of the entire hemisphere we see, a cosmic average that obscures the fascinating details. The possibility of a transient atmosphere adds another layer of intrigue. At its immense distance from the Sun, any atmosphere would be frozen solid, falling as snow to the surface. But as Sedna makes its long, slow crawl toward its closest approach to the Sun thousands of years from now, that faint stellar warmth might be just enough to vaporize a whisper of nitrogen or methane, creating a temporary, hazy shroud for perhaps a century before it freezes out again. Could such a cycle exist? We simply do not know, and what of companions? The search for moons around Sedna has so far come up empty, which is itself a puzzle. Many objects in the Kuiper Belt have satellites, and a moon would not only help us weigh Sedna, but also provide clues to its formation. Was it born alone, or did it suffer a colossal impact that stripped away any companions, leaving it in its profound and lasting solitude? Each answer Sedna provides seems to generate two new, more compelling questions. This is not a sign of failure in our science, but a testament to the object's true nature. It is the very incompleteness of the picture, the tantalizing gaps in our data, that fuels the relentless drive for more powerful telescopes and more sensitive instruments. Sedna is a perpetual invitation, a constant reminder that the greatest discoveries often lie not in the answers we possess, but in the mysteries we have only just begun to unravel. This long-standing mystery is on the verge of a profound resolution, and the key is a revolutionary new eye on the sky, the Vera C. Rubin Observatory, currently being built high in the Chilean Andes, represents a quantum leap in our ability to see the dark. Its mission is breathtakingly simple and impossibly ambitious: to conduct a 10-year-long movie of the entire southern sky. This project, called the Legacy Survey of Space and Time, will use the largest digital camera ever constructed, a behemoth with over 3,000 megapixels, to capture the cosmos in unprecedented detail. Night after night, for an entire decade, it will watch, recording the subtle changes and movements in the heavens. This relentless observation is what will transform the hunt for distant worlds from a painstaking search for a few needles in a haystack into a systematic census of the entire cosmic farm. For every single Sedna we have found with immense effort, the Rubin Observatory is expected to find hundreds, perhaps even thousands of its kin. It will detect these faint, slow-moving dots not by chance, but by design, as its repeated scans make their gradual motion across the sky unmistakable. Each new discovery will be another data point, another dot on a map we are only now beginning to sketch. With a population of hundreds of these extreme objects, their collective orbits will tell a story that a handful of examples simply cannot. The specific patterns in their paths, their inclinations, and their clustering will provide the statistical evidence to finally settle the great debate. Do their orbits align, pointing conclusively to the gravitational hand of Planet 9, or are they scattered randomly, confirming a vast and naturally populated Inner Oort Cloud? The Vera C. Rubin Observatory will not just give us more objects to study, it will give us the language to read the history of our solar system's outermost frontier. This is not merely an upgrade in technology, it is a fundamental shift in perspective, poised to turn the faint whispers from the edge of our solar system into a chorus of voices, each one telling its own ancient story of exile and survival. The deep red world is already receding, its fleeting brush with the inner solar system now a distant memory in its own long timescale. For the next several thousand years, Sedna will continue its slow crawl outward, a solitary voyage into an ever-deepening freeze. Its destination is Aphelion, the farthest point in its orbit, a realm so distant that the sun shrinks to an insignificant speck, just one star among many in a sea of black. It will spend over 90% of its 11,000-year journey in this profound darkness, a silent and frozen sentinel holding its secrets close. This is not a world of dynamic change, but one of near-perfect preservation. The incredible cold, only a few dozen degrees above the absolute lowest temperature possible, acts as a perfect cosmic deep freeze. Every patch of water ice, every complex organic molecule staining its surface crimson, is locked in stasis. There are no geological forces to reshape its landscape, no weather to erode its ancient features beyond the slow, patient bombardment of cosmic rays over eons. Sedna becomes more than just an object. It transforms into a frozen archive, a library whose records date back to the very first chapter of our solar system's story. Its surface is a pristine page, untouched by the turbulent history that shaped the planets closer to the Sun. While Earth's crust has been recycled by plate tectonics, weathered by rain, and scarred by impacts, Sedna's face remains exactly as it was when the planetary construction project finished over 4 billion years ago. It is a museum exhibit curated by gravity and cold, waiting in the silent dark. Its next brief summer, when it swings inward again, will not occur for thousands of years. What will that future inner solar system look like? What civilization might be here to observe its return? And what new tools will they use to read the messages this fossil has carried for so long? The answers are written in the ice on a world that is now turning its back to us, beginning its long and lonely vigil once more. Sedna's story forces us to look inward toward our own sun and then outward to the stars. For decades, our model of a planetary system was based on a single example, our own. We assumed other star systems would follow a similar blueprint, with planets orbiting in a relatively flat plane and a belt of debris not too far out. But Sedna shatters that simplicity. Its existence proves our solar system is not a neat, compact family, but a sprawling dynasty with members living in the deepest, darkest corners of its domain. If our own cosmic backyard holds such vast, unexpected structures, what does that imply for the thousands of other planetary systems we have discovered? The answer transforms how we see the galaxy. Astronomers regularly observe young stars surrounded by bright rings of dust and ice known as debris disks. These are the birthplaces of planets, the raw material of new solar systems. Before Sedna, we might have interpreted these disks as being confined to a region analogous to our Kuiper Belt. But now, we understand they are likely just the visible inner core of something far more immense. The faint, extended glow around these stars could be the signature of their own Inner Oort Clouds, vast reservoirs of icy bodies stretching far into the void, just like the one Sedna revealed around our Sun. This changes the entire narrative of planet formation. It suggests that the violent gravitational scattering that exiled Sedna is not a rare event, but a common phase in the life of a young star system. The processes that built our solar system, the planetary migrations and stellar flybys, are probably happening everywhere. When we model how exoplanetary systems evolve, we can no longer stop at the snow line or the inner debris belt. We must account for these enormous outer shells of comets and dwarf planets, these frozen archives holding the untold history of each star's chaotic youth. Sedna, a tiny world in our own system, has given us a universal key. It teaches us that to truly understand any planet orbiting any star, we must first learn to see the invisible, structured darkness that surrounds it. The architecture of planetary systems is not defined solely by the worlds we can easily see, but by the countless silent sentinels waiting in the cold, each one a clue to a story of creation written on a galactic scale. This profound solitude raises a difficult question about our future. If humanity someday develops the technology to reach these distant realms, who does a place like Sedna truly belong to? There are no flags planted in its crimson ice, no borders drawn across the void. Its existence challenges our very concept of ownership. Current international space law, formulated in an era of closer orbital ambitions, is profoundly unequipped for this reality. The Outer Space Treaty of 1967 states that no nation can claim sovereignty over celestial bodies, declaring space the province of all humankind. But this treaty was written before we knew worlds like Sedna existed, and it says nothing about the resources such a world might hold. Imagine a future where a single corporation or nation possesses the capability to send a craft to Sedna. Could they legally mine its ancient ices for water or extract its complex organic tholins, effectively strip mining a 4-billion-year-old relic for profit? The ethical dilemma is staggering. On one hand, these resources could be the key to sustaining life and industry throughout the outer solar system, providing the water and carbon compounds necessary for survival far from Earth. On the other hand, the act itself would be one of irreversible cosmic vandalism. Sedna is not just a rock, it is a preserved page from our own creation story. To alter it is to erase a unique dataset about the origin of our planetary system, a chapter of history we can never get back. Do we have the right to desecrate such a pristine record for short-term gain, potentially robbing future generations of knowledge we cannot yet even conceive? This forces us to confront our role as a spacefaring species. Are we mere visitors in this vast cosmic museum, tasked with observation and preservation, or are we conquerors, entitled to use whatever we find? The silence of Sedna does not provide an answer, it only echoes the question back at us, demanding that we look inward before we ever venture outward. Sedna's legacy is a powerful reminder that our most profound discoveries often begin with a single, stubborn fact that refuses to fit the established story. This one small world did not just add another entry to the catalogue of solar system objects, it fundamentally rewrote the map. Before its discovery, the outer solar system was a relatively simple sketch. Afterward, it became a sprawling, three-dimensional architectural plan with hidden rooms and secret passageways. Sedna forced astronomers to accept that the Sun's gravitational influence extended into a structured, populated realm they had only ever theorized, pushing the known boundaries of our home system out by orders of magnitude. Its impossible orbit was the key that unlocked the concept of the Inner Oort Cloud, transforming it from a mathematical possibility into a tangible frontier awaiting exploration. More dramatically, the peculiar clustering of Sedna and its kin became the primary evidence fueling the modern hunt for Planet 9, a search that has captivated both scientists and the public. If confirmed, this would be the first new planet discovered in our solar system in over 170 years, and it would all trace back to the questions raised by that single reddish dot. Sedna stands as a permanent monument to the power of curiosity in the face of an anomaly. It teaches us that the most important question in science is not what we know, but what we notice when something does not obey the rules. Every time an astronomer points a telescope at the dark, hoping to find another tiny moving speck, they are following the trail that Sedna blazed, a path that started by asking a simple, world-changing question. Why doesn't this fit? That deep red dot in the void sparks so many questions, and the ones you might be asking yourself are often the most powerful. Could this distant world ever turn into a threat, veering from its path to collide with Earth? The answer is a definitive no. Sedna's orbit is a masterpiece of gravitational stability, locked in a detached and predictable loop that never brings it anywhere near the inner solar system. It is a ship on a fixed course in an empty ocean, and our world is on an entirely different sea. A more haunting question is what you would actually see standing on its frozen surface. The sun from that incredible distance would not appear as a disk you could recognize. It would be simply the brightest star in a perpetually black sky, a brilliant, piercing pinprick of light. You could block it out completely with the head of a pin held at arm's length, and that light, while intense, would carry no tangible warmth. It would feel like staring into a distant, cold laser, illuminating a landscape of deep red ice but offering no comfort against the chill of near absolute zero. What would it be like to look up and see our own familiar constellations, but with that one impossibly bright star that is your own sun? This perspective transforms Sedna from an abstract day to point into a place. It becomes a real location with its own unique sky, its own profound silence, and its own rules of physics and perception. Another common curiosity is why we cannot just build a bigger telescope to see it clearly. The challenge is not merely magnification, but light. Sedna is so incredibly faint that collecting enough of its photons to resolve a surface feature is like trying to read the fine print on a coin from miles away in near total darkness. Our most powerful telescopes are essentially gathering every possible glint of light for years to even create a single, blurry pixel of information. This is why missions like the Vera Rubin Observatory are so revolutionary. They are not just bigger eyes, they are more patient ones, designed to watch for the slow movement that betrays these hidden worlds. By putting yourself in that dark, cold landscape, even for a moment, you connect to the sheer scale and strangeness of this frontier in a way that raw data alone can never convey. From a single moving speck of light to a cosmic cartographer, Sedna's journey has redrawn our map of home. Its discovery shattered the illusion of a simple solar system, revealing not an empty frontier but a structured, populated realm stretching halfway to the next star. This small, red world forced us to acknowledge the Inner Oort Cloud not as theory, but as reality, and its strange path continues to fuel the hunt for a hidden giant planet. It taught us that our solar system story is one of violent beginnings and enduring exile, written in the frozen orbits of ancient fossils. The most profound lesson of Sedna is that we are still learning the basic architecture of our own cosmic neighborhood. The next time you stand under a dark night sky, look up. Remember that beyond the familiar planets, far past the last known worlds, lies a vast and silent ocean of darkness, filled with countless unknown worlds on impossible journeys. Our exploration has only just begun, and the next great discovery, the one that will once again rewrite every textbook, is waiting in the dark for someone to notice its faint, patient